Hi all, let's see the example of multi-instance resource graph. So here register R2, or you can call it as a resource R2, is multi-instance type, and there are two instances present of register R2, and only single instance is present in register R1. And as usual, we have two processes, process P1 and P2. So it is somewhat similar to the previous resource allocation graph. The only difference is R2 register is multi-instance, and we have one more process P3 is added. Okay, so this is multi-instance resource graph. Okay. Now the same procedure we applied to find whether this graph is causing a deadlock problem or not. So first we draw the tabular form. In tabular form we have two columns, one is allocation and the other one is request, and we have two resources, R1 and R2. So R1 and R2 is present as the column section, and we have three different process P1, process P2 and process P3. So P1 covers first row, P2 covers second row, and P3 covers third row. Okay. Now for allocation part, we have to go to the resource vertex and see whether the direction is of edge is from resource to the particular process or not. So here resource R1 is allocated to process P1. So we go to the allocation column in R1 column, and the row is P1, the value is 1, and the other value will be 0. Okay. Now the next thing is go to the resource vertex R2 and see whether R2 is allocated or not. So here the direction of edge is from R2 to P2 as well as R2 to P3. So R2 register R2 or resource R2 is allocated to process P2 and process P3 both. So in process P2 and P3 row, we have to go to the register R2 column and fill their value as 1, and the other value will be 0. Now after filling the allocation column, now let's go to the request column. In request column, we have to go to the process vertex, and if the direction of edge is from process to the resource, then it means the particular process is requesting that particular resource. So P1 is requesting register R2. So here value is 1 and the value here is 0. Similarly, process P2 is requesting register R1. So in P2 row, register R1 column, value is 1 and here value is 0. Now if you see process P3 does not request any resource. Then it means that it says that the value in the request column of particular P3 row is 0 and 0. Okay. Now the next step is finding the current available resource. So current available resource will be R1 is completely allocated to P1, and R2 there are two instances present in R2 resource, but these two instances are allocated to process P2 and process P3. So R2 instance is also allocated. So here the value will be 0 and 0. So currently there are no instance of resource is present, and after that we need to check whether we can satisfy any request of the given three processes, process P1, P2 and process P3. So it looks as if we cannot satisfy the request because the current available resource is 0 and 0. But if you observe carefully here, the process P3 does not request any resource. Here the value is 0, 0. So if we can satisfy the request of process P3, and after satisfying the request of process P3, it will freed up the register R2 value. So one instance of register R2 is now freed up, and the new current available, so process P3 is freed up the R2 resource, so 0 and 1. Now the new available will be, new availability of resource is 0, 1. So based on this new available, we can satisfy the request of process P1. Here it requests 0 and 1. So we can satisfy it. So the next term for process P1 is it freed up resource 1 and 0. Now the new available will be 1 and 1. New available will be 1 and 1. Okay. Based on this new availability, we can satisfy the request of process P2 as well. So finally process P2 also free their resources 0 and 1, and we have available as 1 and 1. If you sum up the availability here, you will get 1 and 2. Okay, and it satisfies the total instance of the different processes. Here R1 have 1 instance and R2 have 2 instances. So here 1 and 2. So this particular graph, this multi-instance resource graph is not present in deadlock. And in this graph there is a cycle which is present between process P1, P2, R1 and R2. And P3 is not contributing in cycle, not present in the cycle. So there is one important point here. In multi-instance resource graph, if there is any cycle present, then we cannot say that definitely it causes a deadlock problem. So here cycle is necessary but not a sufficient condition. Necessary but not sufficient condition for detecting deadlock. So based on these two results, in the previous video, cycle if there is a single instance resource graph, cycle is necessary and sufficient. But in case of multi-instance resource graph, cycle is necessary but not sufficient condition. So you remember these two important results. Based on these two important results, we will discuss the strategy for handling deadlock detection and recovery. So in the next video, we will see deadlock detection and recovery strategy.